we were discussing Fermi theory of beta decay, and in this regard you have seen the first part of this Fermi theory of beta decay previously. Now today this is actually the second part of the lecture on Fermi theory of beta decay. Actually in the first part of this lecture we have calculated a very important quantity, or you can say we have arrived a particular very important result, and that result is for the rate of probability of emission of beta particle from a nucleus. So I have mentioned here the result of the previous lecture. Actually that result will be also utilized in this second part of the lecture. You have seen in the first lecture on this Fermi theory of beta decay that the probability of emission of beta particle per unit time, which you may say the rate of probability of emission of beta particle from a nucleus, and that we have found in the first lecture like this. This rate is denoted by the symbol P of P dP, and that is equal to g square mod of m square over 2 pi cube c cube h bar 7 times a square root of m naught c4 plus c square p max square minus a square root of m naught square c4 c square p square and whole to the power 2 and p square dp. This was the expression which we have calculated in the first part of the lecture. I hope you can remember all the quantities appearing in this expression. You know this G is actually the coupling constant or coupling factor, and M, modulus of M, that represents actually the matrix element of the transformation of nucleus from initial state to final state. Okay, and this P max is actually the maximum linear momentum of the beta particle, or you may say electron, and P is its momentum at any time t. Okay, so this was our result for the probability of emission of beta particle per unit time. Now in this second part of the lecture on this Fermi theory, we are going to find the beta decay lifetime. What will be the beta decay lifetime? We are going to calculate it in this lecture. In fact, you have studied in your lower classes that when we see the disintegration or decay of a nucleus, we define a very important quantity that is called disintegration constant or decay constant. Okay, and every unstable nucleus has a mean time or mean lifetime, you can say, and these two quantities, that is lambda, which is called decay constant, and mean life, which is denoted by the symbol tau, are related to one another. In fact, the decay constant lambda is simply the reciprocal of the mean life. So in case of beta decay process, if you consider that lambda is the decay constant and tau is the mean decay lifetime of this process, then this lambda will be equal to 1 over tau. This is just the relation between lambda and tau. Now in fact how this lambda is calculated, lambda which is called decay constant, actually that represents the rate of disintegration, that is the rate of emission. It means this lambda is actually equal to the probability per unit time for emission of beta particle for the entire range of momentum. It means when you will calculate the probability per unit time for emission of beta particle, when the momentum of the beta particle varies from 0 to its maximum value P max, then that total probability of emission per unit time of beta particle, that is simply equal to the decay constant. So I have mentioned here that the decay constant lambda is equal to probability per unit time for emission of beta particle with momentum values between 0 and p max. Now you can see this expression for p of p dp. This represents the rate of probability of emission of beta particle when its momentum lies between p and p plus dp. So if you want to find the rate of probability of emission of beta particle when its momentum varies from 0 to p max, what we will do? Actually, to get this total rate of probability of emission, we will simply integrate this result defined in this equation A for the limits p equal to 0 to p equal to p max. So just integrating this p of p dp between the limits 0 and p max, you will get the value of lambda. And if you get the value of lambda, you can define the mean life, that is tau. So you can see here that I have written that this lambda is equal to 1 over tau, and that will be equal to what? That is simply equal to integral 0 to p max p of p dp. Okay. Now substitute the value of p dp. You have seen this expression just now, so I am writing here. In fact, in the expression of p dp, this factor g square mod of m square over 2 pi cube c cube h bar to the power 7, this is a constant factor. So I have taken it outside of the integral. And inside the integral, there will be what? There will be a square of this much. This is a square root of m naught square c4 plus c square p max square minus a square root of m naught square c4 plus c square p square and whole to the power 2 p square dp. Okay. Now actually to evaluate this integral, we introduce two parameters. First parameter we denote by the symbol eta, and the second parameter by eta naught. Okay. And how these two parameters are defined? You can see this is just an arbitrary definition of these two parameters to transform this integral into a suitable form. In fact, these parameters eta and eta naught are defined through these equations. P equal to m naught c eta and p max equal to m naught c eta naught. Okay. It means eta and eta naught are the factor by which you can determine the momentum of the ejected or the emitted electron or beta particle. So see here, this is just an arbitrary definition. This has been defined like this to evaluate this integral. Okay. So now use these two results, that is p equal to m naught c eta and p max equal to m naught c eta naught in this equation number 1. You can see m naught c is just a constant factor. M naught is mass of the beta particle, that is electron, that is rest mass, and c is the speed of electromagnetic wave in free space. Okay. So this is these two are constants. So when we will change the parameter p in terms of eta, then the limits will be what? You can see when p is equal to 0 for the lower limit, then eta will be also equal to 0. Okay. So for p equal to 0, eta will be equal to what? That will be also equal to 0. And when p is p max, when p is equal to p max, then you can see that eta is equal to eta naught. So instead of the limits 0 and p max, we will simply write 0 and eta naught. It means at the place of p max, now we will write eta naught. Now replace this p max square, p max, by this expression m naught c eta naught, and this p by m naught c eta. And again at the place of p square we will write what? We will write m naught square c square eta square, and what will be dp? You can see dp will be what? dp, since p is equal to this much, so dp will be m naught c d eta. Okay. So after substituting all these values in this equation 1, what will be the form of this equation? You can see here. So 1 over tau will be equal to g square mod of m square over 2 pi cube c cube h bar to the power 7 integral from 0 to eta 0, and see the expression inside the square bracket. The first term remains at is m naught square c4. Here is c square p max square. C square is at is, but at the place of p max square, you now write m naught square c square eta naught square. Okay. And again in the second term, m naught square c4 remains same, and in the second term is what? This is c square p square. C square is at is, and at the place of p square we can write m naught square c square eta square. Okay. And outside of this square bracket you can see there was what? There was p square dp. So this m naught square c square eta square is at the place of p square, and at the place of dp we have written m naught c d eta n. Okay. Now we take just m naught square c4 as a common factor in the terms inside the square bracket. So the factor outside of the integral is at is, you can see here this remains same, and inside the integral now we take m naught square c4 as a common factor. Since this is inside the square root, so when you will take it out, then its square root will be m naught c square. Okay. And in the first term here there will be 1, and in second term you can see m naught square c4 is already present, and apart from that there is eta naught square, so at the place of second term there is eta naught square and whole to the power half. Similarly in the second factor you can see there will be 1 plus eta square whole to the power half and a whole square, and in outside you can see m naught square into m naught, that will be m naught cube, c square into c, that will be c cube. Okay. And eta square d eta. Okay. Now m naught c square, it is under this square, so this will be m naught square c4, m naught square c4, and in outside there is m naught cube, so this will be m naught 5. Okay. And this is constant, so it is outside of the integral. And this c square, after squaring this will become c4, and here is c3, so this will be c raised to the power 7. Okay. This is simple algebra. And apart from that the remaining factor is this much. You can see this is integral 0 to infinity 0 to eta naught, and 1 plus eta naught square to the power half minus 1 plus eta square to the power half and whole square, eta square d eta. Okay. Now you can see this c cube will now cancel out, and here there will be c to the power 4. So our result is 1 over tau equal to g square mod of m square 2 pi cube h bar to the power 7 m naught 5 c4. And For this integral, which I have just underlined, you can see I have written here f of eta naught. Why eta naught? Because this when you will evaluate this integral, since the upper limit is eta naught, so the value of this integral will be definitely in terms of eta naught. So this has been just written as a function of eta naught. Okay. So this f eta naught has been written at the place of this integral. You can see here in this equation 3 that this f of eta naught is equal to integral this much. Okay. So this is the value, or this is the expression, you can say, for the reciprocal of the mean life of this decay process. Okay. Now see, when we have calculated this mean life of decay of beta particle, we have not think about the Coulombian interaction of the nucleus. But you know, inside the nucleus there is proton, and that proton may exert force which is of Coulombian nature, that is electrostatic force. But for arriving this result, for getting this result, we have never thought about that Coulombian interaction. So definitely this result will be not very concrete, because in calculation of this result we have neglected the Coulombian interaction. So definitely we should take into account the Coulombian interaction too to get the correct result. In fact, you can neglect this Coulombian interaction, but only when the nuclei are very light. That is, if the atomic number of the nucleus is less than 10, and at the same time the electrons emitted are very energetic, sufficiently energetic. In that condition, Coulombian interaction can be neglected. Coulombian interaction can be neglected, but only when you are talking about the nuclei having the charge number less than 10 and the ejected electrons or emitted beta particle are very energetic. Then if you neglect the Coulombian interaction, you are not making a great mistake. You are actually calculating the correct value. But imagine if the nuclei are not very light and the energy and the emitted electrons are also not very energetic. In that condition, you can't neglect the Coulombian field of Coulombian interaction. And in that condition, the function f, which we have considered till now that it is just a function of eta naught, will now also depend on the atomic number of the nucleus. So, in fact, when Coulombian interaction is considered, then the wave function is distorted. The shape of the wave function will change due to the Coulomb field of nucleus. And when we will consider the Coulombian interaction, then this function f, which was f of eta naught, but when we have neglected the Coulombian interaction, that will not know f of eta naught, because now the atomic number of the nucleus will play a great role, because we have seen Coulombian interaction can be neglected, but only when Z is very small. But if you are not talking about the heavier nuclei, in that condition you must take into account the Coulombian interaction, and that Coulombian interaction will depend on Z, because you know if Z is the atomic number of the nucleus, then the charge of the nucleus will be Ze, and this Ze decides the strength of Coulombian force. So definitely in this condition, when we will take into account the Coulombian interaction, this function f will be not a function of eta naught only, but it will be a function of Z and eta naught. So without making any extra calculation, you can use this same result the same result which we have obtained here in equation 2, but simply we will replace this f of eta naught by f of z eta naught. Then the correct value of this mean life, that is 1 over tau, will be obtained in case of the heavier nuclei or when we take into account the Coulombian interaction. So when Coulombian interaction will be taken into account, then what will be 1 over tau? We will simply replace this f of eta naught by f of z eta naught. Okay? So the calculation is very simple. You can see. So in this condition, lambda will be equal to 1 over tau, and that will be equal to g square mod of m square over 2 pi cube h bar to the power 7 m naught 5 c4 f of z eta naught. See the difference. Okay. Now the value of this matrix element mod of m square is uncertain. It is not definite. But in case of most of the allowed transitions means there will be some transitions which will be allowed in accordance with the selection rule, and there will be also transitions which will be not allowed by the selection rule, that is called forbidden transition, that is called prohibited transition. But if our selection rule permits some transition, then the order of the matrix element mod of m square is almost 1. It is its order, it is not its exact value. So this mod of m square you may take of the order of 1, okay, for the allowed transition. And when we will take this mod of m square of the order of 1, in fact in that condition, in this expression you may write 1 at the place of this equation, at the place of mod of m square. But 1 is not its exact value, this is just order. There will be something multiplied in it. Okay. Now this integral in equation 1, see here, in equation 1, this integral, if we consider that we have to evaluate this integral when actually the energy of the beta particle is maximum, that is its energy is actually the end point energy, what will be in that condition? Now we will see it. See here, I have actually mentioned this graphical plot earlier in your previous lecture, that when the relative number of beta particle or intensity of beta particle is plotted in against of the energy of electron, this E is energy of electron, that is beta particle, then the curve is like this, and this is called actually end point. And at end point you can see the energy of the beta particle is maximum, this is E beta max. So if the integral in equation 1 which you have just seen is actually solved, or if it is carried out in terms of this end point energy which is E beta max, actually in that condition it is found that the decay constant lambda is proportional to the fifth power of this E beta max. It means the integral which you have seen in the equation 1, if that integral will be evaluated for the end point energy, that is the energy of beta particle electron is equal to E beta max, in that condition it is found that this decay constant lambda is proportional to E beta max to the power 5. And at the place of proportionality, you can now write the proportionality constant. So lambda is equal to k times e beta max to the power 5. K is actually the proportionality constant. Now let us take the natural log of this equation. So this will be ln lambda, that is log lambda to the base e, and that is equal to ln k plus 5 ln e beta max. Okay. You can see this is just a equation of a straight line. You know, equation of a straight line in slope form is y equal to c plus mx. Okay. So at the place of this constant c, which is actually the intercept on the y-axis, here in this equation is ln k, and at the place of m is actually slope. So slope is in this equation is 5, and at the place of x there is ln e beta max. So definitely, if we will plot a graph of ln lambda in against of ln e beta max, we will get a straight line. Okay, we will get a straight line, but the intercept of that straight line will be equal to ln k. Actually, such graphical plot is known as Sargent's curve. Such graphical plot is known as Sargent's curve, and you can see I have plotted in this figure the graphical plot of ln lambda in against of ln e beta max. And since the graphical plot is just the Sargent's curve, so this actually confirms the Fermi theory of beta decay. Okay, this graphical plot just resemble with Sargent's curve, and therefore we simply say that Fermi theory of beta decay is valid. In fact, in these two straight lines, you can see I have shown by these dots some of the nuclei for which the value of ln lambda and ln e beta max will be what you can see from this figure, and this dot is outside of this line. It means in case of this actinium nucleus, actually there is some deviation, and similarly this Ra for the nucleus RAE, this does not lie on this line. It means it deviates slightly from the Sargent's curve. So these nuclei for which the position is slightly different from this Sargent curve, that will actually give the slightly different value in experiment from the theoretical value. But for most of the nuclei, you can see that those nuclei lie on these straight lines. So almost you can say that the Sargent's curve obtained in this figure actually proves the validity of Fermi theory of beta decay. Okay. So I hope after these two lectures on Fermi theory of beta decay, everything for this theory has been clear to you, and definitely you should watch both of these videos in sequence, and then you must write down these things in your notebook. I have mentioned each and everything, I have mentioned all the languages. So this will be just a very good notes for you for different competitive examinations like university examination and also the civil services examination. And for the competitive examination, you can mark the important facts and solve the objective problems. Okay.